Okay, so what we'll do, let's do a quick, there are a few different topics to cover. So we'll do a quick recap on the things we studied so far. Then, or even before that, or after that, we can speak a little bit about the exam. What you asked for last time is that we use the time to solve previous year's exams. And I think this is fair because part of the time here is defined as a tutorial, and we did not really do that many tutorials, mainly because, I don't know, you didn't ask for it, and I felt that you're doing well with the homework. So we can use the time to, most of the time, to practice on past year's exams. And the alternative is that we get somewhat more deeper into cosmology, or that I try somehow to squeeze more about gravitational waves. I mean, I can do that, but I can write down all the equations, and I think that there is no chance that you really be able to follow me if I try to put it all, to squeeze it all in one lecture. So that's why I prefer not to do it than to do it improperly. But first thing first. Oh, by the way, and then another notice, which should be here recorded so that everybody will be clear. You are supposed to handle the last problem set by tomorrow, I think, or by Saturday evening, the latest. As you know, those of you who ask for an extension, I'm giving extensions. I'm not. I'm trying to be generous, but I want to be clear that the last ones will be the end of June. I do need to grade them. I do need to find time. I have some other obligations to do during the months of July. And so I cannot let you go on forever, and I don't think there is any reason that we go on forever. It's going on with other exams that you may have, etc. So I guess most people that are here do submit your homework on time. And if you're not, or you can tell your friends, you have until Wednesday. After that, I'm not planning to accept homework, except maybe the last one. If you get stuck locally on the last problem set, that can be considered. But if we're talking about previous problem sets, then no, that would be unfair. All right, so this is for the records. Now I haven't done share screen. Let's do share screen. Let's see if it works out, hopefully. Yep. Okay. So just a recap on what we studied so far on a cosmology. So again, since this is something which can be confusing, to be more precise, I was confused when I studied it first. We're talking about really large scales. Everything is that we speak about is relevant not on a solar system scale, not on a galactic scale, not even on clusters of galaxies, but is relevant on scales which are much larger than that. And on very large scales, we know that the universe, as far as we can measure, is homogeneous and isotropic. So we can make up this assumption. And the assumption of homogeneous and isotropic spatial part of the universe. Can you hear me, or there's a problem? So because there is some noise out here which you cannot control too much of. So this assumption leads us to the Robertson-Walker metric, assuming that the spatial part is homogeneous and isotropic, but we are allowed change in time. The Robertson-Walker metric. ds squared is minus dt squared plus a squared t times dr squared over 1 minus kr squared plus r squared d theta squared plus sine squared theta d phi squared. Right? K can get any value, but we're really interested in a -1 for an open, 0 for flat, and +1 for a closed universe. And the scale factor evolution A of t, this is the factor that multiplies all the spatial coordinates. We find by plugging into Einstein's equation. So the scale factor t evolves as a dot over a is equal minus 4 pi g over 3. לא עכשיו, סליחה, אני באמצע הרצאה. Over 3. Rho plus 3p, and a dot over a squared is 8 pi g over 3. Rho minus k over a squared. These two are called Friedman equations. And combined together, we call this Friedman-Robertson-Walker or FRW universe. So we say that the evolution of the universe depends on the energy density, pressure, and K curvature. And then we worked it out, and we found out that sometimes in the past, A of t approached 0, and we call this the Big Bang. In the past, 13.7 gigayears ago. Of course, when A got to 0, then we could not, the theory would have would become invalid, because then we have to consider quantum mechanical effects. But anything above that was valid. So this is the Big Bang. We spoke about the future evolution. The future evolution, excuse me, I have to reshut my door. The noise. The future evolution also depends on the curvature. For open and flat universes, or for universe which is filled with dark energy, we expect it to continue to expand forever. In fact, in an accelerated rate. And if it's a closed universe, it will eventually return to A would eventually return to 0. So that's a function of time, A of t. So for open, well, it should go something like that. If it's accelerating even, there's one open. For flat, it should asymptote. While for a closed universe, we would expect it at a certain point in the future to drop down to 0. That would be called the big crunch. We can in fact calculate when it's going to happen if we know what are the values of rho and p and k. Then we spoke about the cosmological redshift. Right, which meaning that when we are observing a signal, it is from a distant galaxy, it is redshifted. The origin is, of course, that the scale factor A of t has changed from the time of emission to the time that we are observing these photons. Right, so there is a difference between this and the Doppler shift, because even if A of t is at the moment is not changing, we'd still see a change, right? Even if A of t, so let's just define it, right? Omega of t and A of t is constant. And that means that omega 0 over omega 1 is A1 over A0, which enable us to define the redshift Z as lambda 0 minus lambda 1 over lambda 0 over lambda 1, excuse me, which is just A0 over A1 minus 1. A0 is the A value of A today. Now Now, it's not the same as a Doppler shift because it's not that we or the other galaxies are moving. We're fixed. It's the coordinate they change. And it's the ratio of the scale factor A today and the scale factor when the photon was emitted. So even if A is not changing today, for example, if A of t were to evolve something like that, the photon was emitted here and observed today, although A of t is not changing, so right now the galaxy is not changing, we'll still see this redshift. Right. Even in such a case, then the redshift will be observed. Then we spoke about the crucial question of how to measure distances. So how do we measure distances in an ever-expanding universe? And we saw that indeed there is no single way of defining how to measure distance. The two most common, there are actually more than two, but I'm not going through all of them because they're much less, how to say, practical. For practical reasons, there are mainly two main methods that are being used. The first is the luminosity distance. dl squared is L over 4 pi f. L is the luminosity of an object, and F is the observed flux. So this relies on the assumption that we know what is the luminosity of an object. That's a quite strong assumption, but for that we have what we call in astronomy standard candles. Which are essentially objects in which we think we understand the physics, and so we think we understand what is the luminosity, which is emission energy emitted per unit time, right, ergs per second. And the flux is something which you observe. So we can calculate this distance. Now we know that this distance is related to the actual coordinate via dl is the coordinate times a0 times 1 plus that, which we calculate. And another way is the angular distance. Which is when we have an object that we happen to know its size, then we can define the angular distance, So if we're observing an object with some angle delta, let's say it's a galaxy, and we're observing it at some angle delta, then, and we happen to know that the physical size of the object is d, then we define the angular distance, dA, for small angle, as d over delta. And these are not the same, we actually show that. But dA is equal dl divided by 1 plus d squared. So for nearby objects, these are the same, but for distant objects, these are not so much the same. Now, it is most useful when we have, for studying the cosmic microwave background, which we really didn't have time to touch. I have prepared some things to say about that, but I'm not sure that it's the best use of the time. So that's for this angular distance. And then we derive the Hubble's law, which is a relation between the distance, or expressing the distance in terms of something which we can measure. And dl is 1 over h naught times z plus 1/2, 1 minus u0, z squared plus additional terms. H naught is Hubble's constant, a dot over a. today, and Q 0 is the deceleration parameter minus a dot dot over a dot squared again today. So that's Hubble's law. So essentially, this is how Hubble can measure the Hubble have measured, and everyone since then have measured Hubble's constant, right? By making a large sample of measurements of galaxies, measuring the luminosity distance and measuring the redshift. And then we discussed about the evolution of the scale factor. Right, essentially solving Friedman's equations. And we saw that this depends on the content of the universe. Depends on the content of the universe. We have matter, radiation, and vacuum. And we saw that rho matter goes a to the minus 3, rho radiation goes a to the minus 4, and rho vacuum is independent on the scale factor. And now we can make and then we realize that this really tells us that we can divide the history of the universe into different epochs. Sure, what is all this noise? But I told you it's going to be noisy today. I was afraid of that. And that means that while today the universe is dominated by matter, so to be more precise, today we have that omega, right, which is rho over rho critical. Omega total is approximately 1, omega vacuum is 0.7, omega matter is 0.3, omega radiation is 8 times 10 to the minus 5. That means that today, by large, the universe is dominated by matter in terms of the energy content, but it was not always like that in the past. In the past, radiation was dominated. So a very long time ago in the history of the universe, most of the energy was dominated by radiation, and then we can solve Friedman equation. Always solve Friedman equation. There are solutions for the current content of the universe, but we can have a simple solutions if we simply neglect all the other terms and focus on one term. And let's say that it's a flat universe, so we can remove this second term here. And we end up that during a radiation-dominated universe, for a matter-dominated universe, k equal to 0, then we have that A of t is 9/4 8 pi g over 3 omega matter low critical and A0 cube to the power 1/3 t to the power 2/3. And then for radiation dominated, A of t is 4 times 8 pi g over 3 omega radiation rho c A0 to the 4 to the power 1/4 times t to the power 1/2. So we see that the universe started from some inflationary phase, then it went through radiation dominated, expanded as t to the power 1/2. Then the expansion actually accelerated to t to the power 2/3. And when it becomes vacuum dominated, k equal to 0, then it grows exponentially. So we expect the universe to continue to expand exponentially unless something happens around. Now, okay, and then the last thing we spoke about was observational evidence. Went a bit briefly, I think, about some of them. But again, going deep, we can have like spend half of the semester on each one. So basically, there are 5 independent observational evidence. Actually, there is a 6th one, which is the question of why the skies are dark. I don't know if you've encountered this. It's something which goes back to medieval times. Are you familiar with this problem? How can it be that the skies are dark? No? It goes down to maybe something like 13th century monk. I mean, did you think of it for a second? How can it be that the skies are dark?
Maybe the photons from far planets, the redshifted enough so we won't be able to see them.
Now, yes, of course, but before this invention of relativity, right? When people thought that the universe is Euclidean, right? If the stars are evenly distributed in the sky, right? And the light from each star, the flux drops as 1 over the radius squared, right? But if I'm sitting here, I'm dividing the sky into circles, right? Each circle is a radius r away, but then there are the number of stars within this radius will increase as r squared, and the flux from them will decrease as 1 over r squared. So they should cancel out exactly. So the skies in the night should not be dark, but they are. Of course, you know why. Just that you're aware of the problem. Okay, so the observational evidence, except from the fact that the skies are dark, which is obviously because of this redshift and because we know that stars did not exist forever, is our 1, Hubble's law of expansion. The second is the existence of the cosmic microwave background radiation, which was predicted in the 1948, discovered in 1967. That's Gonzalez and Wilson, and then they got the Nobel Prize for that in 78, I think. Again, this goes down to the history of the universe. We said that initially the universe was very small in the sense that very dense. Scale factor was small. And so photons and particles were coupled. In fact, there were just electrons there. As the universe expanded, it cooled down, and then electrons and protons essentially caused atoms. Namely, they recombined into atoms. At that point, they became much less efficient scatterers. So they no longer scatter the radiation. And then when the radiation simply go on, the photons simply continue to go on along geodesics. And they go along these geodesics until today. So we're all surrounded by this 2.7 degrees radiation. In very old televisions, CRT televisions, if you know what I'm talking about, no, you don't, huh? It's these big boxes, like 3-dimensional boxes, not the 2-dimensional boxes, right? That use antennas and not cables to connect. If you are not connected properly, there would be a noise. And there would always be a noise. There is no way of getting rid of this noise because it's a physical noise. It's not something in electronics. There are noises in electronics there. It just tells you how old I am about it. But I know what I'm talking about. You can go to museums and see. Okay, so the cosmic microwave background, this is a T 2.7 degrees Kelvin, and this is the same photons that are there from the Big Bang. The third is called the Primordial Abundances of the light elements. Again, I have a lecture about that, which is pretty nice, but we'll take the lecture, we can do it. It's essentially, as this, it's the same story, right? The electrons and protons recombine, the temperature drops down, so you can calculate what's the probability of them recombining into the lightest atom, which is hydrogen. And there is some probability that they would recombine and form the next lightest atom, which is helium. And then the next one and the next one, right? So this is the deuterium and the lithium, etc. And you can, and these are the building blocks of the stars, essentially, right? Most of the universe, most of the material in the universe combine into hydrogen, and this hydrogen is essentially the fuel that fuels our sun as well as any other star. And that's where the heavier elements are being synthesized. So we can calculate what's called primordial abundances. So the initial abundances of all the light elements. For example, we know that the ratio of helium, so helium-4 over hydrogen is about 1/4, 0.245, and the ratio of the deuterium, right, over helium, and primordial, change since then, is something like 3.6 times 10 to the minus 5, and a few others. And this is something which we can measure. Now there is one thing which is pretty interesting in here. Again, I'll skip that because we want to do more tutorial than actually speaking about that things. But this actually, in the realm of particle physics, that there are various elementary particles, right? Like neutrinos and the Higgs boson, etc. And in fact, this ratio depends on how many generations of neutrinos there are. So we can show you, when we do the calculation, I can show you the calculation. It's actually in my lecture notes. So I don't know, even if I don't do it, you can read this and go over it. This could actually tell you how many neutrinos we expect to see. So this is an independent proof for the standard model of particle physics in some basic sense. If there were more neutrinos, for example, we'd expect these ratios to be somewhat different than the measured values, and that goes back to the calculation of how exactly the temperature changes with time. And at which point the particles which have a certain mass becomes non-relativistic, because each particle has a different mass, so it becomes non-relativistic and basically gets out of equilibrium with the other particles at a slightly different stage in the history of the universe. And so that affects, of course, the evolution of the universe, that affects the exact measurement of the Hubble constant, etc. So we do have here from cosmology, we actually have an independent measurements of some key parameters of particle physics. And so in fact, these fields are tightly connected, much more than some people would imagine, if you don't know it. And then the fourth part is the galactic evolution. As I said, when we look today at telescopes, we see the galaxies far away. We know that galaxies far away are younger, and pretty much like living creatures, they have some sort of a circle of life. And young galaxies, baby galaxies, look different than old galaxies, and as the galaxies age, their morphology change. Of course, it's being done on a statistical way, but we can clearly see that the galaxies that we're seeing in the nearby universe are older than galaxies that we're seeing when we look at the distant universe. And there are ways of quantifying that. So that's another independent evidence that something is changing. And the last part, which again, I didn't really get into because we can spend several lectures on that, is what's called the Bionic Acoustic Oscillation. Here you go. Essentially, as I said, these are acoustic density waves that propagated, that existed in this early universe when it was made out of plasma, of photons and electrons and protons, free electrons and free protons. And there are some density waves, and they just propagated in this plasma, and they could propagate as long as it maintained the plasma. Once it stopped, then they had to stop. So there are some normal modes which were, or the modes that were exactly at the minimum and maximum at the time of recombination. These are the modes that are imprinted as fluctuations on the cosmic microwave background, and this is something which we're actually seeing. And from that measuring these fluctuations, we can actually measure the wavelengths of these modes, and again, tell us a lot about the content of the universe. What was the density back then? What was the fraction of dark energy, etc. So these lengths of this is basically giving us what a standard ruler. This is the largest standard ruler that exists. Something like 490 million light years in today's universe. And so going back, I put a plot on that, right? So this is the fluctuations of the CMB. This is how this cosmic microwave background look like. We're seeing the fluctuations in the cosmic microwave background. So the cosmic microwave background is flat, but there are fluctuations which are of the order of 10 to the minus 5 degrees on that. And what you're seeing, the red areas are areas which are slightly more temperature is slightly higher, and the blue ones are regions where the temperature is slightly lower. We're talking about fluctuations of the order of 10 to the minus 5 over 2.7 degrees. From that, you can expand that in these YLMs and multiple moments, and you can see these dips and peaks from which depend strongly on the ratios of the densities, rho C, rho M, rho radiation, and rho lambda. So this is another independent measurement of the exact content of the universe today. And to summarize, this is the basic picture that we have of the universe. So from the Big Bang until today, initially it was dominated by radiation. Initially you can see that there's this inflation, which is there to explain how come the universe is so homogeneous and isotropic. Although in principle, regions which are far one side never had time to interact with regions on the far other side. And then we're seeing the cosmic microwave background. This is the first signal that there is. After that, there was a period where no light could come to us. So in cosmology, these are called the dark ages. And that lasted until these fluctuations matured into forming the first stars and the first galaxies. And that is believed to occur something like at redshift of between 10 to 20, something like that. So between the cosmic microwave background radiation that we're seeing came at redshift of something like 1200. And in between redshift of 1200 and redshift of 20, there was nothing. And since then, there is this development of the galaxies and stars and planets and everything. And the last addition is that in the last epoch, dark energy becomes the dominant part, and so the universe even further accelerates. So this is kind of, in a nutshell, the basic cosmological picture that has emerged from all these many years of studies. Now, okay, so I have still one part in my lecture notes about the thermal history of the universe and giving the full explanation of how we can actually measure the ratio of primordial abundances. But I think it's not that crucial. So it may be a better use of the time to switch now and talk about the exam. But before we do that, any questions, any comments?
Yes, I have a question. Why, when we solve for radiation-dominated universe and matter-dominated universe, we assume the universe is flat?
We assume the universe is flat?
Yes, we said k equals 0.
Just because it's easier to obtain an analytical expression. Of course, you can get an expression for any value of k, it just may not be that nice and simple and analytic.
Okay, thank you.
And we know that the universe is consistent with being flat, so it's not that I'm lying to you. It's not that it's not, it may be the case, we just don't know.
Okay, thank you.
Do you have any more questions? Okay, so for the exam. Okay, a few words on the exam, and then we go over the exam from last year. Actually was not a standard year. We were asked to give a shorter than usual exam, so I did give a shorter than usual exam. Normally, the exam is planned for 2.5 hours. It will contain 4 questions. At least that's my plan. Again, 2.5 hours. It's planned such that it takes half an hour per question. And so you get an extra half an hour just in case you get stuck. I try to spread the questions among the different subjects that we learn in this course. There are some basic equations which I expect you to know, right? I mean, things such as the geodesic equation is something which you should expect you to know, right? How to calculate the affine connection is something which I expect you to know. If there is a non-trivial equation, you know, the Riemann tensor, for example, this I don't expect you to know. Basically, I would just put it as an equation. We'll see it in a second. I think, you know, the level of questions in the exams are pretty similar to the level of questions in the homework. So if you actually did your homework and you really did it by yourself and you know, you really understood everything and didn't use some friend or somebody else to help you, you really, I don't think there is much to be worried about. Of course, you can get some blackout or anything, but hopefully, you know, you have studied so much during the semester and you worked enough, if you spend enough hours during the semester, then you should not really be too worried about the exam. I don't expect you to memorize too many things, except from things which, you know, we've done over and over again, so that one's maybe yes. The math, I mean, you know, you're expecting, I'm trying to examine your understanding. Right? You will have to solve some equations, obviously, it's not just telling stories, but so, you know, you do need to have the basic skills of how to solve integral. Right? If it's not a trivial integral, then I will give you as a hint what the integral should be like. So you do need to show me that you know your basic maths. You do need to show me that you understand what we're talking about. And I try, whenever possible, to put, you know, some sections in each equation, in each question, so that you know exactly how many credit points you get for each correct answer. I don't want to say that all the questions will necessarily have exactly the same number of credit points, because it could be that some question is a bit longer than the others. And that can give you another hint. You know, if you see how many credit points for each section, that will also tell you how I view it. You know, naturally, if I think that the calculation is a little bit longer, requires some more thinking, then I'll give you more credit points for doing it properly. If it's less credit points, then it means I think that the answer should be quite straightforward. I'm aware of the stress. I'm aware it's an exam. You can make mistakes, etc. But at the end of the day, now it's your turn to show me that you actually understood. I didn't just speak the whole semester, and you got no clue what I'm talking about. The material will cover everything. In principle, everything that we spoke about that appeared in any of the lectures or any of the homework is a legitimate material for me to ask you about in the exam. If there is something that appeared in my lecture notes but I did not discuss it in class, it is not part of the material to be asked in the exam. Remember that my entire philosophy is that my lecture notes are my private property, which I let you free, look at it as part of my wish to help you understand the material. But I'm responsible for that. As far as I don't. If there is a typo or something, it's my problem. What you need to know is not what I wrote for myself. What you need to know is the things that we talked about in class. Questions? Yes.
So there won't be a formula sheet?
Well, normally I don't give a formula sheet. Well, normally what I give is that per question, if I see that there is a formula that is needed, then I just attach it as a hint or something, or as a reminder. Yeah, I didn't say it's normally it's a closed book exam. I think it's easier. If I let you an open book, then it means that I have to ask you questions that you cannot find the answer to in the books. And that can take much longer to solve. At the end of the day, I think writing a good exam is more of an art because it needs to be something which is fair towards all of you, right? Those who know, then they should know. Those who did not study properly, then it should be noted in the exam, and it should be something that I know that those who worked during the semester should be able to solve within the time limit. One last comment which we had is that it's not clear because of something here in the physics department. It's not yet clear if this exam would be considered an official exam in terms of the Mador Bchinot, the exam part, or it will be called an internal exam and then not just pass the grades to whoever needs to get them. There is some subtle. It wouldn't really matter for you. I guess it will exam date from what I got is I think it's the 20th of July. I don't remember what time. It's gonna from your perspective, I don't think it matters. What I said at the beginning and what I wrote holds. The exam will account for 80% of the final grade. Homework that you did, you're doing will count for 20%. There will be a repeated exam if any of you would want to. Of course, my goal is that nobody will want to because I have no wish to sit down and write another exam. But that's more up to you than up to me. But just think of it that in that sense, I'm on your side. I have no wish to write another exam and grade another exam. I much prefer that nobody will want to have a second exam. But having said that, that does not mean that everybody is going to get 100. You will have to show me that you know the material. And the exams, I think, are fair. I never heard students that were complaining that the exams were too hard. I never heard any student saying that the exam was ever too easy. But, yeah. Any more questions about that? No? I hear that you're saying, I see that somebody is saying that you're saying something, but I cannot hear you. So maybe your microphone is going off. Anybody want to say anything? Neta, I was talking to you actually. Did you want to say anything?
אולי עכשיו שומעים?
עכשיו שומעים, כן.
רציתי לשאול, הטופס של המבחן באנגלית, בעברית, אכפת לך?
Okay, yeah, the exam. So yeah, the exam will be in English, right? Now there is, I'll show you that in a second. Since it's in the Bar Ilan, there is some title which I have to go through. But the questions will be asked in English. You can answer in English or in Hebrew. That's the two languages that I can understand your answers. Don't try any other language. Oh, no, because I won't understand what you say, what you write there. But you know that I'm not examining your English skills. I'm examining your knowledge in general relativity. Personally, I find studying in English somewhat easier because everything is from left to right, and everything is, you know, all the parameters have reasonable naming, etc. More questions about that? No. Okay, so as promised, this is how it looked like. This is the exam that was there last year. As I told you, this was shorter than usual exam, and it was easier. The way I made it easier was rather than asking for 4 questions, as I normally hope to do, I asked for 3 questions, and I gave 2 hours rather than 2.5 hours. So this is how it looked like last year. There were 3 questions. You saw I gave some basic. I hope that they're going to stop, otherwise it's not going to end up very well. So let's go over the questions and then let's start to solve them one by one. So the first question, you're given the Schwarzschild metric, the one that you know. You see that I actually give it so that you don't need to worry about that. And then I ask you the following. A particle moves along a geodesic in this metric. Write an explicit form for the conserved energy, E, along the particle's trajectory. Hint, you may want to use the properties of a time-like Killing vector, and for clarity, add a constant m to the equation for E, where m, of course, stands for the mass. Part 2, let us assume that the particle moves radially. Argue that at r goes to infinity, where the initial velocity of the particle is assumed to be 0, we can set t equal to tau. Using the result you derived in the previous section, deduce an expression for the t over the tau that is valid at all points along a radial geodesic path. Then I said, hint, recall that the tau is related to the s by a constant. And then part 3, using the results you obtained in part 2 above for the t over the tau, calculate the particle's inward coordinate velocity, v, the r over the t, as a function of the coordinate radial distance, r. Show that when r approaches the Schwarzschild radius, r Schwarzschild, which is given, v approaches 0, implying that it takes an infinite amount of time, or the coordinate time is measured by a stationary observer at infinity, to reach rs along the geodesic. Hint, you may use the metric compatibility for massive particle, which is also given here. And question part 4. In order to explore the vicinity of a black hole, an astronaut is dangled at the radial coordinate r above a black hole of mass m. How far above the black hole must the astronaut be held so that its clock runs exactly half as fast as the starship, which is a long distance away? Hint, is the zeroth component of the velocity of the, U0 is the zeroth velocity of the astronaut, t over the tau. Oh, sorry, it's a question. Is the zeroth component of the velocity of the astronaut U0 equal to t over the tau, the same as the one calculated in part 2 above? If so, then why? Okay, we'll go over that shortly. As you may see, we really did this in class. You just have to remember what we did in class and basically repeat the derivative that we did in class. Pretty much all of it. We'll go over that shortly. Question number 2. Consider a metric of this form, G mu nu, where the 0, 0 is minus f of some of y, and then the rest is 1s on the diagonals and 0 everywhere else. Where y here is specifically the y coordinate, and fy is some as yet unknown function. And it's given that we know that at the origin, f of 0 is equal to 1. Now I ask you, what are the conserved dynamical quantities of the metric? And then I ask, a particle moves in a metric starting at the origin, where the metric is locally Minkowskian, with an initial form momentum in the x direction, which I put in boldface. At some later time, the particle is at location L, having coordinate L with x, y. What is the P2 component, i.e. the y component of the form momentum of the particle at this point? What is the y component of the momentum of the particle at this point? Express this in terms of the initial particle's energy, E, which is minus P0. And then part 3, using the result from the previous part, compute d P2 over d tau, express the result in terms of the particle's initial energy, E, mass m, as well as f of y and its derivative with respect to y. And part 5 is compute all the non-zero components of the affine connection of this metric. So I actually give you here the formula. And the last part, you are given now that the actual functional form of f is f of y is 1 plus ky squared, where k is some constant. Describe the initial non-relativistic behavior of a particle that is placed near the origin. As a hint, I actually give you the formula for the affine connection, so you don't even have to remember it by heart. Okay. This is a question of, well, we'll work out the solution. And then question number 3, I give you another interesting metric, considering the 3-dimensional space-time. So now it's in 3D. ds squared is a minus 1 minus r0 squared over r squared dt squared plus dr squared plus r squared minus r0 squared d phi squared, where r0 is a constant. We're only interested in the region r greater than r0. So the questions are, how many Killing vectors does this space have? I guess you should be able to answer right away without even thinking. The second question is, write an expression for the observed quantities associated with the Killing vectors you found in part 1. So what are the conserved quantities? The third question is, calculate the gravitational redshift experienced by a photon emitted at R1, which is greater than R0. Propagate radially and observe that radius R, which is R2, greater than R1. And part 4 is using the metric compatibility, which I even give it to you again here. Write down the equation for time-like geodesics. I give you a hint, what is epsilon for time-like geodesic? And part 5 is, what is the condition for circular orbit in this metric? And I give you a hint, write the equation you derived in the previous sections in terms of the potential and find its extrema. All right, who wants to solve first? Which question do you want us to solve first? Yeah?
Let's start with question 1.
Start with question, which one? I did not hear you. What did you say? That's not fair. Which question? The first question? I'm sorry, I cannot hear you. Did you say the first question or the second question? I wasn't sure.
Yes, the first one.
The first one. Okay, so let's go in order.
First.
Okay.
Yeah, let me spell.
Sorry? Okay, who wants to solve? One, guys. Who wants to solve? A particle moves along a geodesic in this metric. Write an explicit form for the conserved energy. Let me get something, because I think I do it like that, somebody told me something. I can do something like that. Maybe not. So I can open up this. Right. That's what I was hoping for. Okay. So now I have the questions here. And then some, oh, you can see them, right? And then let's look at the solution. So how would you solve part one? Fine. Write an explicit form for the conserved version. Yeah, go on.
That metric.
Sorry?
It would be just to develop the killing vector of that metric.
Exactly. So which killing vector?
So there would be the killing vector for the conservation of energy. So that would be about the time coordinate.
Exactly. Very good. So we can write down the energy, right? It's just K mu. Oh my goodness, dx mu over the tau, right? And then K mu, remind you, is just a 1, 0, 0, 0. So K mu, just K mu, G mu nu. We actually have the G mu nu, so this is just minus 1 minus, it's here, right, so it's minus 2 GM over R.
So don't we need the next minus on the first equation?
Sorry?
It's all good.
Don't we need an extra minus on the first question on the first equation?
No, I don't think so. Wait, 0, 0, 0. Right. Do we have an extra minus? Yes, there is an extra minus there. Sorry, you're right. And so we write down that energy to be, well, I said add up the constant, so the constant would be m. Put it will be mc squared, 1 minus 2 gm over r. So we can put the c squared, if we put the c squared over there, and then it will be dt over d tau. That's the first. That's the answer to the first question. So you see that if you know what you're doing, it takes exactly 2 minutes to solve. Now let's look at the second question, the second part. Let's assume that the particle moves radially. Argue that as r goes to infinity, we can set t equal to tau. Using the result you derived in the previous section, there's just an expression for the t over the tau. So what happens when r goes to infinity?
Metric becomes the Schwarzschild, the Minkowski metric.
Particle becomes a Minkowski. As a result, you must have the dt over the tau is equal to 1. So what is the energy?
MC squared.
MC squared. As we all know, right? Now,
could I go the opposite way around? Say I would start from the expression for the energy, and then when I would say when r goes to infinity, the term of the r goes to 0, and I know that I would say that E equals to mc squared, but then it wouldn't take into account that my body that the particle still could be moving. So is it possible that I could have gone from the other way around?
not sure that I understand what you mean by the other way around.
I'm trying to say, like, instead of looking at the first of the metric and then deriving what E would be, I'm trying to think, well, if I look at this expression of E, and now I assume that R goes to infinity, so what's inside the brackets goes to 0, right? I mean, it goes to 1. It just goes to 1. Then I would be left with E equals mc squared dt over d tau. And then what I would want to say is that since E equals to mc squared, then I can cancel out the both of them, and dt is equal to d tau. However, that would not be taking into account the fact that the body might still be moving and not resting.
No, I'm not.
So how can I say that E equals
no. There's no motion here. Right. What I'm looking now.
But why not? Says that let us assume that the particle moves radially.
Sorry, no. Sorry. Yes. Wait. What I want you is to calculate deduce the expression for the t over the tau, right? Which is valid at all points along the radial geodesic path, right?
So I cannot achieve that. I cannot achieve that from dt over d tau.
I don't see how. I mean, so what you want to say? Okay, so let's say that t is equal. This is the general expression here, right? This is a general expression for the energy.
Yes.
Now I want you to get an expression.
Now I'm saying.
Over the tau. Now, if you do it like that.
Yes. So now I'm saying that that R goes to infinity is 0.
Yeah. What is 0? You mean the.
And so I'm left with E equals mc squared dt over d tau. Yes, exactly. And then all I'm left with is E equals mc squared.
But what you want is to add up this term here. But this expression is true only when R goes to infinity.
Yes.
Now, what I want to do, let's finish what I'm doing.
Yes,
and maybe it will get clearer, right? What I want to use the fact that the energy is conserved quantity. I mean, you can do whatever you want as long as you do it properly. The easiest is to use conservation of energy, to my opinion. Right? Now, you know that this is the general expression for the energy. You know that at infinity, right, you don't need that because at infinity, dt over d tau is equal to 1. And I actually give you that as a hint, right? Say that, argue that R goes to infinity, we can set t equal to tau, right? It's actually written here. And in that case, E is mc squared. And then I can use the conservation of energy to write down the t over the tau. So, this combined with this, the t over the tau is just 1 minus 2 gm over rc squared to the power of minus 1. It's an expression that is generally true.
So we say that when the particle is at infinity, we can assume that it's at rest because we have nothing to compare its motion to.
Okay, I agree with you that possibly the way it's being phrased may be a little bit confusing. The idea of this section is simply to use the conservation of energy. And yes, I assume that the particle is at rest at infinity. I did not assume it has an extra kinetic energy.
I see. Okay, thank you.
Okay. Now part 3. Using the result you obtain in part 2 above for the t over the tau, calculate the particle's inward coordinate velocity, the r over the t, as a function of the coordinate radial distance r. Show that when r approaches the Schwarzschild radius, or Schwarzschild, v goes to 0, implying that it takes an infinite amount of time to reach rs along the geodesic. Now, in fact, here I ask you to repeat the same calculation that we really did in class. This is slightly lengthier, you can see that, but it's not that much lengthier than the previous one, right? So, using the metric compatibility, right? we have, right? We said it's a radial, so the theta and the phi are we can neglect them, they are 0. So we only have the r and the t here. So we have a -1 equal g00, so it's a -1 minus 2 gm over r dt over d tau squared, right? Plus 1 minus 2 gm over r minus 1 dr over d tau squared. If you want to be precise, then you can put here 1 over c squared to get the same units for r and t. But you can say c is equal to 1 anyway. So now we're asked to get the velocity, and the velocity is the r over dt. Now we have the r over d tau. So we can write down the r over d tau, so chain rule. The r over d tau is just the r over dt, dt over d tau. And so we get a -1 is equal to dt over d tau squared times -1 minus 2 gm over r plus 1 minus 2 gm over r minus 1 times dr over dt squared. Now we make use of the result we derived above, of dt over d tau. So inside the parentheses, we have a -1 minus 2 gm over r plus 1 minus 2 gm over r minus 1 dr over dt squared is equal to minus 1 over dt over d tau squared, so it's just 1 minus 2 gm over r squared. Yeah?
Saf,
Yes.
can I take you back to the first part of the question, part I?
Yes.
I think I missed what you did here. I mean, why is it true, the term for E?
Well, we derived that in class.
Yeah, I looked for
I
that.
refer you back to my lecture notes, which appear on the you have access to on the web page. Right. This is a conserved quantity. I said that with any Killing vector, there is a conserved quantity.
Yes,
and
I know.
Conserved quantity associated with the time-like Killing vector, we call it energy. Right. The fact that you can say it's an interpretation. In some sense, you're right. Mathematically, that goes down to Netter's theorem, stating that every conserved quantity, any symmetry of the metric has a conserved quantity. And the symmetry of nature has a conserved quantity. So a symmetry in time has a conserved quantity, which we call energy. Right?
And you assume you have symmetry in time?
I don't assume, I see it from the structure of the metric. Right? This is something which we discussed. So this is something which, if you don't feel comfortable about, you better better go and review this, right? If you look at the Schwarzschild metric, how many Killing vectors does the Schwarzschild metric has? Admits. We say that the Killing vector exists whenever there is a symmetry, namely the coordinates are independent, the G mu nu is independent on some coordinate, right?
Yes.
Now, we see that G mu nu, G00 depends on R. So we don't have a symmetry in the radial direction, right?
So it's only T and phi.
Right. So the symmetries we have are for T and phi, right? And since the choice of phi was somewhat arbitrary, we can choose it wherever you want. So we really have four independent Killing vectors. One of them associated with symmetry of time, and three associated with the rotational symmetry. Right? We can rotate three dimension. Now, two of the one associated with the symmetry in time we call energy. And the three associated with the symmetry of rotation, these are really implied conservation of angular momentum. Angular momentum is a vector, so we have two, direction and magnitude. In the direction we just specify, that's essentially what tells us that all the motion in Schwarzschild metric is on a plane. That's why all the stars, they're rotating the sun in the plane. And the magnitude just means that we cannot get too near or too close, too near or too far from the sun. Yeah, you with me? I thought we thoroughly discussed that in one of the classes. I don't know which one, but it's all recorded, so we can go back and check it out.
Yes, thank you.
No, that's serious, because if you don't feel comfortable about that, that is something which I definitely expect you to know by now. If you don't feel comfortable, now is a good time to grasp it. Now, I'm not going to hold it against you in any way, right, guys? Now is the time to ask all these questions. Now is the time to do the review. We have nearly a month before the exam. There's still enough time. I don't know what other things you have to do, but there's still enough time to make sure that everything is clear. And I will take questions. If you ask me by email something you're not sure of, I will answer. But review this material. This is something which you're supposed to know. Okay. I'm taking it very seriously. I don't know who asked, because some of you don't use cameras for unknown reason to me. It's okay, guys?
Yes, thank you.
Okay, so we're in the middle of answering part 3, right? So I just made use of the result in part 2 to write down an equation like that. So what to do next? Right. So you simply divide by this part, by this term. So you have -1 plus 1 minus 2 gm over r minus 2 dr over dt squared is equal to -1 minus 2 gm over r. So it's really a plus here. So the -1 and -1 cancel. And we have the r over dt squared is 2 gm over r times 1 minus 2 gm over r squared. Or the r over dt is square root of 2 gm over r times 1 minus 2 gm over r. obviously, when R goes to RS, which is 2gm, then the second term goes to 0. And goes to 0, which is what we thought it would be. Right? And the first term just becomes 1. So you see, if you know what you're doing here, it's something like 1, 2, 3, 4, 5 lines of calculation. So I'm trying to design the question in such a way that if you know what you're doing, you can finish it all in 1 hour. Okay, and then the last part. In order to explain the vicinity of a black hole, an astronaut is dangled at the radial coordinate r above the black hole of mass m. How far above the black hole must the astronaut be held so that his clock runs exactly half as fast as the starship, which is a long distance away? Now I'm asking you a question here. Is the zeroth component of the velocity of the astronaut u0 the same as the one calculated in the part 2 above? What do you say? Is there a difference between this part and the previous 3 parts?
Well, can't you use why don't we use the expression for the conserved energy?
Why not?
What?
Why not?
No,
There
I'm
is
saying that we should.
Yeah. Okay.
That we can just take the part for the conserved energy, plug in the value of the energy that we know that will satisfy our equation, and from there we can find out what how far away must we be.
I assume you can, but there's very risky. It's likely that you make a mistake if you do it like that. In principle, you can do it, but there is a big difference. This is a question which really is not so much about the calculation here. It's more about seeing it. What is the difference between this part, the question in this part, and the question in the first part?
That now we are at a constant radius.
Yes. Now the particle is not moving. So it is not along a geodesic. Now the particle is held fixed. Somebody has to hold it, right? So the particle is an astronaut, right? Somebody has to hold the astronaut, because if you don't hold the astronaut, it will just follow along the geodesic. Right? You cannot just stay there, right? You have to fall in. Right? It's like floating in the air above the earth, right? Something must hold you, otherwise you're simply falling. Right? So it's not that immediate to use the same calculation that we did before. If you try to do that, you could do it properly. I'm not saying not, but you have to be extremely careful in noticing the difference here. Right? So we say that as opposed to the previous part, the astronaut is not moving, but held fixed. fixed radius. Fixed R. So we can calculate this ratio directly from the metric. We can simply use the metric. And use the metric for R equal theta equal phi equal constant. We have the tau over dt, right, is a minus the s over dt, right? It's actually written there. Or it's not written there, but you may remember that, right? It's just a minus the s over dt. So it's just square root 1 minus 2 gm over r. Inside of this needs to be equal to 1/2. So 1 minus 2 gm over r is 1/4. 2 gm over r is 3/4. And so r is equal 8 over 3 m. So this is the radius. So once you realize the difference, the calculation is immediate. It's not so much a question in mass as much as a question of understanding what happens. Okay, let's go to question number 2. So I think you're seeing the idea, right? I mean, you have several sections here to solve. Each one, if you know what you're doing, is a few lines. If you know what you're doing. If you got more than a few lines, then likely you were doing something wrong. Sometimes I see that, and it's a pity because sometimes it's happened to very good students. You get stuck on some calculation, you spend a lot of time. It's a pity because then you're losing a lot of credit points. The tips I can give you, if you get stuck, it's the usual ones, right? Go to the next question. And if you get something which got really weird, I mean, remember, I'm not expecting you to do like very long calculations in an exam. Another tip which is general, and that I should tell you, right? I thought it's kind of general, but it's always worth the same. Always explain, follow the basics. Always explain what you're doing. Don't just tell me the answer is 5. You won't get any credit. I mean, if it's not 5, you're not going to get any credit at all. If it is 5, and I don't know why you think it's 5, then you're also not going to get the credit. Always explain what you're trying to do in words. Use. I have to face that all day. Use words. Now I'm calculating that. Explain in words what you're doing. You will get credit for that. Even if you do something wrong in the math, then I will know that what you're trying to do. I could find out where something went wrong. Okay, question number 2. So, what is the conserved dynamical quantities of this metric? If given this metric, what's the conserved dynamical quantities?
Could say that it would be this a displacement along the x and z axes,
right.
And energy.
Very good, right? So since the metric is independent, the metric is independent on time, x, and z. So the conserved quantities should be P0, P1, P3. Momentum, well, P0 is the energy. These are the conserved quantities.
What about rotations? How can I infer any symmetrics about rotations?
You can, but you don't see it right away from that, I guess. Well, you know, if you answer what I wrote, you get full credit because this you get immediately from the metric. Now you can have angular momentum in the y direction, but you don't really need to do that. Okay, I'm running a little bit because we're running out of time. So a particle moves in the metric starting at the origin, where the metric is locally Minkowskian, right? F of 0 is 1, so the metric is locally Minkowskian, with initial form momentum in the x direction, right? At some later time, the particle is at location L, which have coordinates x and y. What is the P2 component, the component of the y component of the form momentum of the particle? And express it in terms of E, the particle's energy, which is minus P0. So what is the form momentum? So initially, what is the form momentum of the particle?
MC squared px00.
The particle. Well, I would write this p squared is p mu. So it would just be minus m squared. Minus m squared c squared, essentially. Now we know that P0 is a minus E, because I gave it to you. So P0 is an upper index, right? It's just G00, P0. So G00 is the inverse of the metric, so it's 1 over F. It's a minus. So it's E over F of 1. Now the momentum in the x direction is conserved. Because there's nothing that will prevent it from conserving. Right? So P1 of L squared is P1 of 0 squared, and just E squared minus M squared. And then at the point L, right, we have P0 squared. I see that I missed a square here on my note. Okay, it doesn't matter. P0 squared, so E squared over F of Y squared minus P1 squared right, minus P2 squared is just M squared. So P2 squared is E squared over F squared of Y minus E squared. That's it. Yeah?
Stop. Why is the P1 of 0 squared is E squared minus M squared?
Because initially the particle starts to move in the X direction. Right? It says it only has a motion initial for momentum in the X direction. Right? So we only have motion in the X direction. The momentum is just E squared minus M squared. Momentum squared, of course. And it's all in the X direction.
And we know it's that with velocity 0, so we can say it's mc squared.
No, it has a motion. If it is not a motion, it stays at the same place.
So why can we say it's mc squared and not gamma mc squared?
Well, you can say it's a gamma mc squared, but you don't need to. Right? That is really go back to the special relativity part. We just say E squared is equal to M squared plus P squared. Right? This part really asks you to review your knowledge in special relativity. Sorry for that. Yeah?
Yes, thank you.
Now, say using the results from the previous part. Let me see, did I miss anything here? Okay, using the result from the previous part, compute dp squared over the tau, dp2, sorry, over the tau. Express the result in terms of the particle's initial energy E, mass m, as well as F, Y, and its derivative. Okay, so that's pretty much straightforward, right? Just taking that equation and derive it. Right? So it will just be 2 P2, right? dP2 over tau, right, is minus E squared. E is constant, so and then this would be F prime minus 2 divided by F cubed 1. And F prime is the F dy, so dy over tau. But dy over the tau is just P2 over M. So P and P drop down. 2 and 2 would drop down. So we have dP2 over the tau is just minus 1 over M E squared over F cubed of Y. Right. So that's pretty much straightforward. Okay, we pretty much run out of time. Number 4 is to compute all the non-zero components of the affine connection. I can give you what are the affine connection, and the calculation is pretty straightforward. And number 5, you're given now that the actual functional form of F is that, where K is some constant. So describe the initial non-relativistic behavior of a particle that is placed near the origin. The basic idea in number 5 is to write down that near the origin, well, it's actually based on number 4, because when you do number 4, you find out that most of the affine connection components are 0. In number 5, you find that gamma 2, 0, 0, which is 1/2 f prime, is 1/2 2k times 1 plus ky. And near the origin, it's approximately k. So that means that near the origin, the particle will feel some acceleration in the minus y direction, which is very consistent with what we have here, right? We have here an acceleration in the y direction. So the particle will feel an acceleration of strength k in the minus y direction. Okay, number 4 you can do right away. Okay, I'll post that on the course webpage. I'll put that, and I'll put the exam from 2 years ago. So you can have a look at those. Okay, I mean, it's not hard. You see that each question, if you know what to do, is very simple. I think the difficult part is that lies in the fact that I'm trying to get up questions from different parts of the course. And it's not an easy course, as I guess you'd agree with me. So you actually, to get a good grade, you actually need to know very well GR. Getting, most people that work don't have to worry. But to get like a 95 and above, I'm very happy to do that. It's not that I'm against that. I'm actually happy to give good grades, but you actually have to show that you're good. Sometimes it happens. Those who get it are exactly the students that I'm looking for to continue to do masters and PhDs. So if you're interested in that, I told you that. Feel free to come to my office. You know where I am, or to drop me an email. Those of you, I know I recognize some faces. Those of you who are here knows that there is a pretty nice group that is doing pretty cool stuff around with what I do. I'm not sure how much you're familiar with that, but we do really cool stuff, which is definitely related to that and to emission and injection of materials around black holes, but that's not part of the course. Anyway, any further questions? Okay, I do want to ask you to fill in the student's evaluation form, if you haven't done so already. If you don't have any more questions, again, when you study towards the exam and you have questions to ask me, please feel free to do so. Don't wait until the last moment. I'm very busy with many other things. So if you wait until the last minute, I may simply not be available. Okay? It's been a pleasure. Enjoy the weekend. Enjoy the rest of the semester, whatever is left.
Thank you very much.
Hope to see you all in the near future. I'm stopping the recording now.